Hey everybody, this is going to be a quick demo video looking at how we can use Jupyter and Python to do some data splitting sorts of tasks. So I'm going to use it to run you through a few intuitions about why we do this kind of thing, and also at the same time demonstrate very manual ways to do this kind of technique, and also some more automatic ways that scikit-learn can manage for you. All right, let's get right into it. So we're working here with the same kind of toy problem that we used the last demo. So there is some data which we are going to be able to generate synthetically, right? We're going to create some toy data, which is going to be from some predefined function. And in our case, once again, let's use this linear function. Okay, so let's go ahead, generate that. And now that we've done that bit of setup, let's take a look and see what happens when we generate some of this data. So here's 10 data points drawn from the line function that we passed in, with some corruption by some Gaussian noise, right? You can see the underlying data there, the underlying function which is generating the data in green, and there is the blue data points which are the corrupted noisy version of that green line. And then there is a red linear regression fitted on top of those blue data points, right? We're using here the same thing that you saw the last time. We take the x values and we generate a polynomial degree 1. If you remember what that is, that means we have two columns now. One column is the bias term, number 1, and the other column is going to be the x values that correspond to the x values of those blue dots. Okay? Then we're going to create a linear regression using scikit-learn, and whoops, that's the rest of the, sorry, that's the xtrain and xpredict going through the polynomial features. This is where we're going to generate a linear regression and train it up using ordinary least squares on the bias term plus the x term. Okay, because we have built the bias term into our inputs, we don't need to tell scikit-learn to fit a separate intercept. If we didn't pull in the bias into the x matrix, then we would say fit intercept equals to true. All right, exciting. This is the part where we get to actually see that red line. So we have some xpredicts that we generated, which are just very fine data across the x-axis. And we're going to get the predicted y values at each of those data points. And that generates our red line, okay, right here. Okay, so there's some data. And you may note that before we generated this random data, we set the random number generator seed equal to 1, 2, 3, 4, right? So that means that every time we run this, we're going to get the same result, but it's because of that random seed that we get a particular roll of the dice. Well, let's do the same thing, but let's this time use a different random seed. So because there's a different seed for the random number generator, we're going to get a different set of Gaussian noise to corrupt those same points. Okay? So nothing has changed in the second cell except what the random numbers generated are going to be. So let me try to get both of those in frame for you. So it looks to me like in the second plot, the noise randomly is a lot less noisy, right? We're drawing from the same noise distributions, we're just doing different rolls of the dice, and randomly those noises seem to have smaller magnitude on average by my eyeball meter, and that is leading the line of regression, the fitted line of regression in red, to be a lot closer to the green line, which is the true function. But nothing else changed in the cell. It's just a copy of the previous cell except for that random number. Well, let's keep going with this idea. What if we use another random seed, 42? Well, this is entertaining. Looks like the slope is almost spot on, but it is offset. The bias term is a little bit different clearly this time around. All right, one more. And we see yet another version of the same thing, right? Random seed changes, our exact noise that goes into this changes. Even though we still have, in all cases, the same underlying generating function, we're getting reasonably different lines of regression out because those random noises change the exact nature of the training data. Okay, well, this is kind of fascinating here. Oh, look, I gave myself even one more of these to do. I won't belabor the point, except that apparently this one I selected last quarter because it's remarkably close to the true generating function through random chance, even though it has some actually rather large excursions in the magnitude of the noise. Okay, so we've seen this multiple times. We get the same function going with different noise. We get very different results. So this is a model for what goes on in the real world. Okay, you get data, which is a measurement of some process you want to understand better or you want to be able to predict. That process is assumedly got a true underlying thing happening, and that might be corrupted by noise. It might be corrupted by noise because measurements are imperfect. It might be corrupted by noise because you only have a small random sample of a much bigger population, right? So there's various ways in which random processes are going to cause your data to vary each time you go after collecting it. So logically, we expect the same result to happen if we draw a giant, well, not giant, let's just say bigger than 10 data points, which is what we've been doing, right? If we draw bigger than 10 data points, and instead of drawing 10 points repeatedly, we just draw 100 all at once, and we block it up into essentially cross-validation, right? Where we're only using a smaller chunk of the full data to train up at any given time. Okay, so let's take a look at this. I shouldn't have said cross-validation because that's not what's happening right here. But instead, we're just going to use 1/10 of the data at a time. And we're going to get the exact same results we just did, right? So here we draw 100 samples. Okay, here are 100 lovely samples of data. Okay, we're going to break them up into chunks of 10. And the way we're going to do that is perhaps quite important because I know we do this on at least one homework. So here are the numbers 0 to 100. Now we're going to randomly shuffle those numbers so they're no longer organized 0 to 100. They're now going to be like 87, 14, 12, blah, blah, blah. Okay, we're just going to take the first 100. Sorry, my bad. We're going to take chunks going from 0 to 10, then 10 to 20, and then 20 to 30, or more particularly 0 to 9, 10 to 19, right? I gotta be exact when I'm talking about this stuff. 20 to 29, right? And then we're gonna get these indices. Okay, so you can see here what happens. Here is our shuffled data, 0 to 100 in a random order. And so here is the first chunk of that data. Here's 10 data points, which are now completely randomly assigned into the first fold, so to speak, here. Okay, here's data points, 10 to 19, and so on and so forth. Okay, so let's use each of these 10 sets of 10 data points to plot their own lines of regression and see what we get. Okay, so here are 0 to 10, 0 to 9, 10 to 19 plotted, 20 through 29 plotted, so on and so forth, all the way down until we get to 90 through 99. All right, so you can see just by scrolling here that we've got, differences, but it's hard to compare all 10. So this time around, I'm going to take the same lines of regression, those same chunks of 10, and we're going to plot them all on top of each other. So here is the graph that I really wanted to show you. Each one of those draws of 10, its fitted line of regression on top of the true line of regression. So there are 10 red lines, each one from the same underlying process, but a different random noise went into the data that fitted the line. And underneath all that in green is the true generating function for the data. So you can see that there is quite a lot of diversity in those regression lines. And if you wanted to know something like, okay, I've got some random data, it comes from a random draw of some bigger population, what do I think the true population's line of regression would be if I could somehow magically measure the whole population? You can do exactly this process. Do this thousands of times. Take thousands of subsamples or resamples of your data, and you'll generate shadows, and you can say, okay, what's the middle 95 percentile of these slopes? And what's the middle 95 percentile of these biases? And you can shade in everything in here and say, okay, this is all highly likely to be the true population regression is somewhere inside this 95% confidence interval that I've made through a Monte Carlo simulation here. But that's all a digression. That was not what I wanted to talk about today. What I do want to talk about today is the diversity of these lines. Okay? So we could easily see that we can get some pretty different results just from random variation. So the more of these lines we made, the more the variance would probably be up to some limit, right? Like if you just took the 100 data points and we divided it into not 10 chunks, but if we divided it into 5 chunks, we would have slightly less variability because more of the data would go into each one of the folds, each one of the chunks, right? Because more of the data goes into the chunks, there is a better estimate of the true population inside that chunk, right? This is straight up central limit theorem. The more data you get, the better your estimate is going to be. All right? So you're going to have less variability because all of the chunks have got a better estimate. It's by virtue of dropping from a 100 sample size down to a 10 sample size that we get this crazy variability in these lines. Okay, so if we had 5 chunks instead of 10, we would have less variability in these lines. They would all lie closer to the true green line. Okay, so what about if we take all of the 10 lines and we somehow take their mean of slope and mean of their bias? Well, that's what we see in this second cell here, right? Took the same chunks of 10. We got now the mean coefficients instead of all the coefficients, and we put them into this cyan line. So you can see the ghost of the red here, right? Using a skip of 10. And you can see that the fitted line of mean coefficients lies closer to the generating function than most of the red lines. So what if we do what I previewed earlier? What if instead of skipping by 10s, we skip by 5s? Do the same thing. Okay? So now, oh, whoops. I said it wrong again. Okay, so instead of taking 10 10s in my 100, what if I take 25s? So opposite direction, we're going to have way more variability because now we only have 5 data points to try to draw an inference about the population, right? So now we see that these red points look quite a lot, red lines look quite a lot more variable than these red lines. Okay, so smaller sample size, more variability in the estimate, bigger sample size, smaller variability. Now we're finally at what I was trying to say earlier. We're going to take chunks of 20 at a time, which means we only have 5 folds. So now finally, this is what I was saying. And you can see that there's much less variability here. Okay. What was it, again, that I wanted you to take home from all this? So let's say you have a data set. You've downloaded 100,000, I don't know, what are we working with here? Downloaded 100,000 images of digits from the MNIST data set, okay? And you can do your cross-validation on the data such that you have either in each fold 10,000 images, or you can do it such that each fold has 50,000 images, okay? So at half of the data, it's a trained test. It's just 2 folds, okay? Or you can take 1/10 of the data as the holdout set. Or you could even go crazier and go smaller, right? The more folds you make, the smaller the number of data points used for training. Sorry, opposite direction again, man. So with cross-validation, the smaller the number of folds, the fewer data points you use for training. Okay, so in that case, you're going to have more variability in your answer in every fold. But you can recover some of that variability if your answer is the mean of all of those folds. Okay, so going back to the that lecture on cross-validation, the way in which we do that is we take the validation error in each validation fold, but we don't use any one of those folds as the estimate of the generalization error. we look at the mean across all the validation folds to be our test set error, right? So that is going to, with small fold size, so just 2 folds train test or 3 folds in a cross validation, you're going to be using less of the data, and therefore you're going to get more variability in the estimate fold to fold. But you can recover that variability by taking the mean. Okay? Flip side, when we use relatively few samples held out, right, which means in a cross validation, a high number of folds. So there's a lot of folds. So we only, if we take 1/20th of the data set and hold it out, we've got 19/20ths for our training every time, right? So that's where we see ourselves in this kind of a situation. Each fold is relatively the same, right? This would be a relatively small number of folds where each fold has a holdout, which is quite large in size. Okay, but the examples here are very extreme, right? Because we're working with only a handful of samples for each one of these linear regressions. But the principle holds true in general for realistic sized data sets. All right, so what have we just illustrated there? This is something called the bias-variance trade-off. We are totally going to talk more about this several times during the quarter. But fundamentally, you get to do one of 2 things with your data, or your choices of algorithms, or a whole bunch of other things you're going to do in machine learning. You're going to choose bias, or you're going to choose variability. And they are almost always a trade-off in the choices you make in machine learning. So in this case, I've been talking specifically about splitting up your data, right? But you're going to find this again and again. So you can choose the low variability version, or you can choose the high variability version. All right. So let's go on to the next section, which is about, I don't want to do all this stuff by hand. Let's use scikit-learn to make it easier. Well, so for doing the splits of data, one of the easiest functions you can import from scikit-learn is train test split. And it does exactly what it says on the package. Okay? You want to take the data and turn it into 2 chunks. One you're going to use for training, and a completely separate chunk that's never touched for training, which you're going to use for testing. Okay? The way in which it works is pretty easy to see, right? You just turn in all the data. You tell it, for instance, one way you can run it is you can just tell it what fraction of the total data the test set will be. Okay, so in this case, we're going to use 1/3 of our data for testing. So here you can see in blue all the training data, which is going to be 2/3 of 50 data points here. And in the yellow, you're going to see 1/3 of 50 data points as the randomly selected test set. Now in this setup, it does randomly select, right? It doesn't take the first third, it takes a random third for the test set. Okay. Well, let's do some things where we've tried to use these test sets to better understand what is the performance level, what is the generalization ability of this linear regression we're going to make. Okay, so we fit everything into degree 1 because that's what we're doing. We're going to use our model and fit it on the training data. Big surprise. And then we're going to get the predicted line of regression now that everything is hunky-dory, we're going to use the trained model to predict, sorry, didn't want that one. We want, oh, sorry, this is training set error. That's why I got confused, right? So what we're getting here is the fitted line of regression, and this is the mean squared error of the predicted line here, which is in red, versus the actual training data, okay, which is in blue. So this line of red, what is the mean squared error, the fitted line of regression, versus the blue data points, okay, the training data. And we can see here that what we fitted has not got zero error, right? We didn't lie straight on all those data points. We have a mean squared error of 0.19. Okay? Well, generalization error says that we're probably going to do worse than this when we go to test data, right? So we have already fit the model, so we don't have to run them, we don't have to fit the model again. It's been already fit on that training data. So now let's run it on the test data. And that's what happens in this line. We take the model that's already trained, we give it new data, and we ask it to predict the y values. Right? So let's do that. Okay? So the fitted line of regression in red and the true generating function in green are the same in these two figures, right? What's new is that here we're going to throw on top of it the yellow test data, which this algorithm has never seen before, right? And we're going to use this line here to calculate the mean squared error between the red line and the yellow dots. And as you see, we've got something like 50% more error, 0.3 versus roughly 0.2, right? So as predicted, we do worse in generalization than we do on the training set, because in the training set, we are overfit to the noise in the data, right? Or at least we're able to learn stuff about it. Okay, so now let's take a look at a brand new kind of problem. Okay, we're going to use we're gonna grab 10,000 data points, right? So we have so many data points from the same population now, right? So what we have here is well beyond our test set, which was what, like 20-ish, I guess, a little less, right? So our test set was kind of small-ish still, but now we've grabbed 10,000 data points from the same process. In a sense, this is probably a pretty accurate picture of the true population. And we can see that the actual generalization in this new data set is something that's not as bad as was predicted with our 20-some points above. Okay? All right. The final thing I wanted to show you is the procedure to use scikit-learn to do k-fold cross-validation. All right? This is about as simple as it gets here. So you can declare a k-fold cross-validator. You tell it how many k. And the procedure to do the training is that you're going to need to collect all the predictions as you go through the folds. Right, so we're going to generate ourselves some empty lists to fill up as we go. And in each fold of the cross-validator, we're going to get a list of the training data points and the holdout data points. Unsurprisingly, we're going to fit our data on all the training data points. And we're going to predict on all the holdouts that it's not trained on. And we're going to append that prediction onto the end of our empty array. And we're going to loop over all 5 folds. Right? At the end, we have to flatten these arrays because they actually end up being lists of lists. And we just need a flat list. And then we're going to calculate the mean squared error on all the holdout data sets. Okay, so here we find with 5-fold cross-validation an answer which is a little bit nicer. Oh, sorry, it's a little bit closer to, yeah. So it's a little bit closer to our quote-unquote true generalization error from our 10,000 sample, right? That was 0.25. Our cross-validator 5-fold is 0.24, which is a better estimate than our cruddy test set, which said 0.3 in a rather pessimistic way, right? Okay, so what have we learned? We've learned to do things the easy way and to do things the hard way. And the purpose of walking you through all that hard way stuff was to try to give you some intuition about how random noise can affect each fold of a cross-validator or each new data set, okay? We've also talked a little bit about the idea that there is something called the bias-variance trade-off, and that you're going to be making design choices in both procedural, like this in the data splitting world, and also in your algorithms in the way they work, that are going to trade off bias, which is just being a systematically underestimating or overestimating kind of thing. We're going to always be more pessimistic, maybe, than the true generalization error, versus variance, right? If we give up our biases, then we're going to get a lot more variance in every fold of what we're doing. And if we give up our, if we want to get rid of variance, we're going to have to accept some biases in return in our estimates. So again, we'll clarify more about that as we go on, but I want you to kind of start that idea rolling in your head, and we're going to point it out a lot as we go. All right, everybody. I've rambled on far too slowly for far too long. I hope you all enjoy playing with this notebook, which of course you can run directly from the GitHub on Colab. Hasta la vista.